Hello, after in the previous session we talked about how we can determine phase composition and relative amount of each phase for different system, including the Eutectic system. Now we will see how microstructure is developing in a Eutectic system. The first case is when the concentration or the composition percent of tin atom is below 2%. So B for this line, and we will see what's happening in the microstructure of the system. Of course, at higher temperature, where we are dealing with the liquid phase, we only have this one phase, and the composition weight percent is 2. If we continue cooling down, then we reach to this phase, region in which we have two phases, liquid, and of course we will see alpha solid regions are also appearing. And if we continue cooling down around 300, 200, so on and so forth, we will see only one phase, which is alpha solidus, and the composition weight percent of tin is the same as shown here, so 2%. Therefore, at room temperature, somewhere around here, we expect to see polycrystalline with grains of alpha phase that has a C0 composition. Now we move a bit to the right. From this point we move to the right, where the composition percent of tin is between 2 and 18.3. so before we reach to this point. So again, here in the liquid phase, of course we will have only one phase, and the composition weight ratio is C0. If we cool it down so that we reach to this phase region, of course now we will have liquid phase, and small regions are now turning into solid, they solidify, and they form alpha phase. These regions are becoming more and more, and if we cool it down to about 200 degrees Celsius, now we see a consolidated solid region. It's all alpha, and of course the composition ratio weight percent is C0. If we continue cooling it down, now we fall in this region that we have two phases. One phase is alpha, and now we see the beta phase, which is solid, is also, or solid region is also appearing in the form of small tiny regions, as you can see here in a red color. Of course, the beta phase, which is mostly tin, because we have very few percent of them, we only see small tiny regions as shown here. Of course we are expecting to see more regions of beta when we move to the right. So in summary, in this region, especially at room temperature, we have alpha and beta range. We have polycrystalline with alpha grains and small beta phase particles. Also bear in mind that this region is only small portion of the whole phase diagram in which we have a small weight percent of beta phase. Now we move to the eutectic point, where we see a composition weight percent of tin to be almost 61.9%. Again, here in the liquid region, we are dealing with only one phase, that is liquid, and the composition weight percent of tin is the same as the composition of eutectic point, 61.9. Okay, we cool it down up to this point, 183 degree, and nothing happens. We only deal again with a liquid phase region up to this point, and there is no change occurring until we reach the eutectic point or eutectic temperature. When we reach to the eutectic temperature, of course now we have a transfer. The liquid transforms into two phases, alpha and beta phases. This transformation can be also shown in the form of liquid. Upon cooling is transformed into alpha. It's with a weight percent of here, which is almost 18.3, and the beta phase, which with a weight percent of almost 98% here. Just correct myself, alpha phase has 18.3 weight percent of tin, and beta has almost 98 weight percent of tin. Now, during this transformation from liquid to two new phases, right below the eutectic point, we have a redistribution of the lead and tin components, because both alpha and beta phases have different composition, and none of them is liquid. So we will have a redistribution which is done by atomic diffusion. The microstructure of the solid that results from this transformation consists of alternating layers. So alternating layers, as you can see here, this is called also lamella of alpha. So one is alpha, blue is alpha, and red is beta phases. That both of them they form simultaneously at the same time during the transformation. The weight percent of the alpha phase, as I said, is 18.3, and for the beta phase is 97.8, almost 98. The microstructure that is resulted from this transformation is called eutectic microstructure. You can see this micrograph from lead tin eutectic microstructure. As you can see, lamella that are formed below the eutectic point or eutectic temperature. The lamellar formation is also shown schematically here. It represented the formation of eutectic structure for lead tin system. Direction of diffusion of these tin and atoms are indicated by blue and red arrows, as you can see here, and the eutectic growth direction is shown by the big red arrows. Now we move back to the concentration weight ratio, composition weight ratio, which is above 18.3, this point that we did it before, and which is below 61.9, which is eutectic point. So we want to see what's happening here. Of course, in the liquid region we have only one phase, liquid, and the composition weight ratio is C0, say 40 here. If we cool it down, this phase region, we have two phases. We see small regions or patches of alpha solids, which is in the liquid. Here we see bigger regions that are solidus, alpha solidus. If we want to find composition of the weight percent of tin in the alpha region, just go to the left, all the way to the left, until we reach to the or intercept with alpha, just above the eutectic line that is intercepting or coming from the eutectic point. The alpha percent, the weight percent of tin is 18.3 in the alpha phase. For the liquid phase, it is it can be found from this green one right above the eutectic point, and 61.9 weight percent of tin. The weight ratio can be found using the Lamellar rule by this relation, which is 0.5, and the liquid ratio, weight ratio can be found from, or weight percent can be found from this relation if we deduct this value from 1. So we see the same weight ratio at this point here, just above eutectic point. If we go right below eutectic point, now we see this kind of microstructure. Of course, we have lamellar eutectic, as we discussed in the eutectic part, and we also see these regions of primary alpha. So this is the microstructure that you are expecting just below eutectic point. To find weight percent of Sn. You just go to the left, it is the same value, 18.3, the same as before, but for beta it goes all the way to here for the second phase, and the value is 97.8. The weight percent for alpha using Lamellar rule is 0.73, which result in 0.27 of weight percent of beta phase. It's called primary alpha. These regions are called primary alpha because it's formed prior to crossing the eutectic isotherm. Based on what we went through in the eutectic point, we are expecting this lamellar eutectic microstructure, as you can see here. And the left side, which we know as hypoeutectic point, right below the eutectic point to the left, when we have lower composition weight percent of tin, we see again the eutectic lamellar microstructure plus regions of primary alpha. The same thing will happen in the right side of the eutectic point, which is known as hypereutectic, and again we expect to see lamellar microstructure, which is related to eutectic microconstituent, and these phases now, these regions are now beta, no more alpha. The phase region is not always in a form of area. As an example, in intermetallic compounds, we see that they exist as a line on the phase diagram, not an area. And this is because the composition of the compound is a fixed value. So therefore the region between liquid and this intermetallic phase is composed of both of them. The same for this region, so on and so forth. As we discussed, we have one of the invariant points in the phase diagram is eutectic point, in which liquid transforms to two solid phases. So upon cooling, we have a liquid that is transferred to solid phases, alpha and beta as an example, and by heating, then we have one phase, liquid phase. This is happening for lead tin at 183 degrees Celsius, where there is 61.9 weight percent of tin, as we showed it in the previous slides. There are other invariant points in 3 different phases. These include Eutectoid. In Eutectoid point, one solid phase transforms to 2 other solid phases. As you can see, one solid upon cooling is changed into 2 solids, and by heating, then these 2 solids are transformed into 1 solid. An example is in carbon ion phase diagram. So where phase gamma upon cooling is transformed into solid phase alpha and intermetallic compound cementite, and this is happening at 727 degrees Celsius with this weight ratio. The other invariant point is Peritectic, in which liquid and one solid phase transforms to a second solid phase. So as you can see, solid plus liquid upon cooling is changed into another form of solid. An example is again in carbon ion phase diagram, what's happening in almost 1500 degrees Celsius at the weight ratio of 0.16% carbon. Phase delta and liquid upon cooling is changed to phase gamma. The other invariant point is congruent. Congruent point where there is no change in the composition. In other words, for incongruent transformation, at least one of the phases experience a change in composition. Now let's see an example of Eutectoid and Peritectic point. In Eutectoid, we are expecting to see a solid which is changing upon cooling is transformed into two other solids. Look at this point E. We have solid delta, which is transformed into delta plus epsilon upon cooling. So this is what we are expecting. This is the transformation reaction that is happening in Eutectoid point. The other point is Peritectic, so we have to look for a solid and liquid which is transformed to another solid upon cooling. So look at this point. So we have a solid and liquid, and then it's transformed, this one, solid and liquid, is transformed into delta upon cooling. So this is an example of Peritectic transformation. Now let's have a look at the iron-carbon phase diagram and to see if we can recognize the invariant points and how the microstructure looks like. Look at first we look at the Eutectic point. Of course, that's the minimum, a point that has the minimum melting temperature. And if you remember from the previous slide, upon Eutectic, point A here is the Eutectic point, and we have a liquid phase which is transformed into a solid, two solid phases, gamma and cementite upon cooling. The other point that we can recognize is this point. You see gamma phase, which is known as also austenite in iron-carbon phase diagram. Upon cooling is transformed into alpha plus cementite. So point B is what we know as a Eutectic point. Here, of course, in the gamma phase, we will have all gamma solid phase, and this is shown in the form of grains. Upon cooling, now we have two phases, in which this region is the alpha phase, which is soft, known as ferrite, and we have also cementite part, which is shown in form of hard layers of red. This pattern is also called in the microstructure, as you can see here, is called perlite, which is alternating layers of alpha and cementite, ferrite and cementite phases. Of course, we can find the weight percent of each of these phases using tie line. And the orange line here is also showing the temperature of Eutectic point, which is 727, and this is the temperature of Eutectic point, which is 1148. And now we move to the left side of the Eutectic point, where we know as Hypoeutectic steel. So if you look at this region here, we only have gamma phase or austenite. We go down, and now we see small regions of alpha solidus, and if we continue, we see alpha solidus are regions becoming bigger and bigger, and the gamma austenite, similar to the previous slide that was shown for the Eutectoid point, it will be composed into perlite parts. So we have soft alpha or ferrite region shown in cyan, and we have hard red lines or red parts that are made of cementite. So this is the perlite region that is actually created inside the gamma regions. And this is what's shown in the microstructure of the same system under microscope, which is showing perlite structure and pro-eutectate ferrite. To find the weight ratio, of course, we can use tie line as shown here. The weight ratio of alpha phase is S divided by the total value, and the weight ratio of gamma phase here is 1 minus W alpha. For here that we have a microstructure of perlite and ferrite together. The weight ratio can be found from the tie line again. We have the weight ratio of perlite is the same as gamma, but for the weight ratio of alpha we have S divided by the total value, so we can find it by measuring this distance from almost 6.7 to almost 0.3. And in order to find the weight ratio of cementite is equal to 1 minus the weight ratio of ferrite, alpha ferrite. Now if you move to the right side of the eutectic point, where we known as hypereutectic region like this one, of course in gamma we have solidus gamma phase. Now we see small regions are changed into small regions of cementites are showing here. By cooling it down more, we see regions of cementite as shown here, and if we continue again we see gamma region is transformed into perlite. The next subject is Gibbs phase rule, in which it's actually represents and propose a criteria for the number of phases that they exist in a phase diagram at equilibrium, and is shown by this simple relation in which P is the number of phases present, F is the number of degrees of freedom or the number of externally controlled variables like temperature, pressure, and composition. C is the number of components. Usually we deal with 2 components. As an example, what we had in lead and tin together. And N is the number of non-compositional variables like temperature and pressure. As an example, for one phase, the value F can be calculated as this because temperature is the only non-compositional variable, so N can be inserted as 1 because we have 2 compositions usually, so C is 2. And if we are dealing with only one phase diagram like alpha, beta, or the liquid region, then in that region the number of phases is 1. Therefore the degree of freedom can be calculated as 2. This means that to completely describe the characteristic of any alloy that exists in one of these phase fields, we must specify 2 parameters. These are composition and temperature. We can do similar steps to find the degree of freedom for a 2-phase region. If we do it for a 2-phase region, when we have 2 compositions, then the value of F, or degree of freedom, is 1, so it means either temperature or composition is enough to completely define the system. As an example, we can completely know about the composition of this line if we only know the temperature. So the composition of alpha and liquid phase here is actually dictated by these extremes, Cl and C alpha of the tie line. Let's have a look at this example for a phase diagram of carbon ion. Just below the eutectoid points, we want to determine the composition of some of the phases. We want to know the amount of these phases, and we want to know the amount of perlite in the 100 gram of the alloy. So we can work it out in the class and talk about it in the class. This is a summary of we went through in these 2 sessions. So this was what was presented about chapter 11 phase diagram. Thank you.